Hello and welcome to the military episode of the International Society of Explosive Engineers web series Explosives Every Day, which looks at how explosives are used in a wide range of applications. I'm Alistair Torrance, President of the ISEE. Our organisation started in 1974 when a group of like-minded people got together in Pittsburgh, Pennsylvania to discuss how to better apply commercial explosives and how to champion the blaster in the field. Move forward to today and we're an international organisation with more than 4,000 members spread over 90 countries with a mission to advance the science and art of explosive engineering worldwide. We do this through sharing our knowledge and providing training and education for everyone involved with blasting. We also have a strong education foundation and have awarded more than $1 million in scholarships to our students in our industry. Before we get started, I'd like to thank our series partners Dyno Nobel, OPIT Blast and LDE Global. This series would not have been possible without their tremendous support. So today's episode takes a look at some specialised uses of explosives in military settings. Our military sponsors are RMAG and APT Research. Here's a little bit more information about them.
Since 1969, Loki Corporation has been providing the U.S. military and commercial clients explosive storage magazines and explosive storage containers of all sizes and varieties for use all over the world. We are proud to have consulted with the U.S. Navy in the 1980s when they developed what are now the Type II U.S. military specifications. With a wide range of customizable options and sizes, ranging from 8 square feet to 5,000 square feet, RMAG has a storage solution for every application.
APT Research is an employee-owned small business based in Huntsville, Alabama. APT provides professional engineering services in the explosives regulatory compliance, risk management, and safety fields to government, military, and commercial customers. APT works routinely with commercial explosives regulatory bodies, such as the ATF in the U.S., and has expertise in assisting commercial explosives companies with the pursuance of site licenses, either by meeting quantity distance rules or through pursuing a variance based on risk. Other APT services include training and access to APT-developed software tools, IME Safer and Safer, explosives testing, planning, and support, general explosive safety training, hazard classification support, regulatory standards, and criteria development.
This episode's presenters are Denis Rickman of the US Army Engineers Research and Development Center and Jason Baird of Loki Incorporated. Denis Rickman is a research physicist in the research group Engineering Systems and Material Division, Geotechnical and Structures Laboratory of the US Army Engineer Research and Development Center, where he leads research initiatives in the general areas of explosion effects, blast loading, and development of demolition methods. He has degrees in geophysics and engineering mechanics and has been involved in the publication of over 130 technical papers and 5 patents during his 37-year career in explosive effects research. Denis will give us an overview of the applications of explosives in military-related research and development. Jason Baird is a retired Air Force B-52H navigator, rocket scientist and retired professor of mining engineering with advanced degrees in aeronautical engineering and mining engineering. He owns and operates Loki Incorporated, a small business that provides engineering services to the explosives, propellant and pyrotechnic industries and related activities. Additional capabilities include ballistics, blast mitigation consultation, and design and legal expert witnesses services. Jason will discuss the considerations required to effectively defend civil structures against attacks by gunfire, explosives, and vehicles. It's going to be a question and answer session with the presenters right after this presentations. The panel will discuss many questions that were asked by a live audience at the time of this episode's first airing.
I'm Denis Rickman. I'm a research physicist, and I work for the U.S. Army Corps of Engineers, Engineer Research and Development Center. My everyday activities include planning and managing explosives-related research projects. Also do a lot of blast-related data analysis. I started out in this area, sort of accidentally in a way. I graduated with a degree in geophysics. Thought I was going to go out and explore for oil, and this actually wound up being the first place that I could find a job. And it's really been a fun career for me. One of the things that tells you that it's a pretty good job is I've been doing this for about 35 years, and I'm still not bored. So still doing new and fun things every day. Just a brief overview of the Engineer Research and Development Center, or ERDIC. And as you can see on the map, there are a number of laboratories and field offices primarily in the eastern half of the U.S. And again, the ERDIC headquarters is located in Vicksburg, Mississippi. And we also have a field office in London. And the ERDIC is the research arm of the U.S. Army Corps of Engineers. ERDIC has a number of science and technology core competencies, and those most closely aligned with the application of explosives in R&D are the areas of blast and weapons effects on structures and geomaterials, and civil and military engineering. Most of the explosives used in military R&D fall into one of these categories. Munitions, such as shells, bombs, or mines. Bulk high explosives, such as C4 or TNT. And bulk blasting agents, such as ANFO or ammonium nitrate and fuel oil. Military R&D primarily consists of the following areas: weapons testing, blast loading of weapons platforms, blast loading of protective structures, research of blast phenomena, and the collection of forensic weapons signatures. In terms of weapons testing, blast weapons must be evaluated to quantify the actual explosion effects produced. And the explosives used consist of any of the various munitions, such as bombs, missiles, or artillery shells that are being evaluated. In this case, we're evaluating the effect of a rocket-propelled munition. And if this looks fun, I have to admit, it is pretty fun, especially when you hit the target. And here we have some examples of airdrop munitions being evaluated, both in terms of explosive output and their capability to penetrate into various targets. And here we have a shaped charge warhead being evaluated. And you see the explosively formed jet propagating to the right and penetrating through the steel plate. Now we'll talk a little bit about blast loading of weapons platforms. Designers use numerical modeling to assist in the development of new weapons platforms, such as vehicles, aircraft, or ships. But that modeling can only take them so far. And so prototypes of these platforms are subjected to testing in order to verify their performance against various blast threats. And the explosives used in this case could be any of a number of different munitions. Also, in many cases, bulk blasting agents such as ANFO might be used to provide the prescribed blast environment. In this case, we see a relatively large ANFO charge that was detonated to produce a prescribed air blast loading for the vehicles and objects you see on the test bed. And it's interesting to note that that sort of bubble-like feature that was moving outward from the blast is actually the air shock wave created by the detonation. And in this case, we're subjecting a surplus armored vehicle to an explosive blast. And another armored vehicle subjected to blast, in this case in conjunction with blast testing of a generic surrogate hull. And all of this testing is done in conjunction with numerical modeling, again to provide the very best details regarding optimization of the vehicle design. And now moving on to blast loading of protective structures. Designers use sophisticated modeling to assist in the development of protective structures as well. Both subscale and full-scale prototypes of these structures are frequently subjected to testing in order to verify their performance against various blast threats. And as we saw for the vehicles, any of a number of munitions, such as bombs, missiles, or mines, might be used as the explosive threat. And again, larger threats may be replicated with a blasting agent such as ANFO to provide the necessary blast environment. In this case, we see some expeditionary shelters subjected to an air blast load. And here we have various structural elements being subjected to high pressure, close proximity blast threat. And now moving on to research of blast phenomena. Although explosives have been in widespread use for a long time, many areas of blast phenomenology are still not fully understood. And so researchers continue to use a combination of numerical simulations and experiments to explore critical aspects of blast effects. And the explosives used may be high explosives such as C4 or TNT. Also, various explosive mixtures are detonated to study explosive-specific effects. And in this case, some basic cratering testing, also known as the easy way to dig a hole. And here we have an explosive storage magazine that is being evaluated at subscale. And so even though this is probably at around 1/4 scale, we still see a relatively large explosive charge and pretty impressive results. And now moving on to the collection of forensic weapon signatures. Blast weapons and improvised explosive devices, or IEDs, are detonated in carefully controlled conditions in the presence of witness items such as metal or concrete plates, and also vehicles, signs, and other common targets. And then we observe the damage to these items, which are then cataloged to aid in the forensic analysis of explosive attacks. And the explosives used could be any of a number of munitions, also improvised explosive devices of various designs are detonated to study their specific signatures. And in this case, we see an explosively formed penetrator, or EFP, weapon directed against an armored vehicle. And this is a particularly nasty little device. And here we have a simulated vehicle-borne improvised explosive device detonated, and you may be able to see that there are a number of vehicles and even telephone poles and things of that nature in the testbed area, and the damage to those items is correlated to the observed levels of blast, and then that allows us to correlate the damage to a particular threat. Okay, now in closing, I'd like to present what I call the explosive testing top 5 quotes. Number 5, failure is always an option, albeit not a very good one. Number 4, did you take my truck up to the roadblock like I asked you? Number 3, there are no shortcuts when handling explosives, except the ones that pass too close to the morgue. Number 2, explosion physics, like math, only louder. And the number 1 explosive testing quote, we're pleased to announce we are still here to report the results. I think we're going to be using explosives for military applications and research and development for the foreseeable future. So many different explosive mixtures coming out all the time, new weapons, new platforms, new structures that and new threats that have to be evaluated. And again, been doing this for a long time, and I'm still doing new and interesting work all the time. So I think there's a bright future in this area.
I'm Jason Baird, President of Loki Incorporated and Emeritus Associate Professor in the Mining Department of the Missouri University of Science and Technology, otherwise known as Missouri S&T. My day-to-day activities include working on a contract with the Army's Space and Missile Defense Command on a small business innovation research project having to do with pulse power. I also do legal consulting and expert witness work for several law firms that are involved in cases in courts involving explosions. I do engineering consultation on energetic materials, on defense against ballistic attack, armor systems, and security facilities and security preparations for nuclear power stations. Last but not least, I do the day-to-day maintenance and work on my lab and my ranges on my property. Started out in this industry by a non-voluntary posting by the Air Force when I was an officer, just as I'd finished my Master of Science degree in Aeronautical Engineering, specializing in gas turbine propulsion and materials and high-speed aerodynamics. Turns out the Air Force needed a propulsion engineer to try to figure out what was wrong with the solid rocket engine on a system called the Advanced Medium Range Air Missile that was under development at the time. So they posted me in that position. I didn't really know anything about it because that wasn't my background, but I was very fortunate to have some of the best minds in the world in the area of solid propulsion that were able to help me. We solved the problem, and as a reward, I was also given the warhead to work on. Turns out there were some problems with that also that we got solved. Eventually, when I left that position, I was the Air Vehicle Branch Chief. Stayed in that sort of area, solid, liquid, nuclear, and chemical propulsion in the Air Force during my career. And so the Air Force, I guess, forced me to become an energetic materials engineer. And after spending a couple of years upon my retirement from the service as a junior high science teacher, I decided to take Paul Wurzy up on his offer to come and be a grad student and get my PhD at the then University of Missouri-Rolla, which of course now is Missouri S&T. Had to get my PhD in mining because back then we didn't have a PhD in explosives or a master's in explosives. That was something that we created after I got on board there. And I spent a little over 15 years at the university working directly either as a research scientist or as an associate professor in the Department of Teaching. Now, why do we still use explosives in the military? It seems like kind of a silly question, but really explosives are what we call a force multiplier. One person can do far more damage to the enemy and to the enemy's resources and facilities using energetic materials than one person using either ballistic or kinetic energy weapons. So from that standpoint, I don't think the services are ever going to not want to use energetic materials. The key things are that we, just as in any other explosives engineering field, we have to work safely, and safety is paramount. And one of the ways we do that is by using risk-based and risk analysis-based training, as well as practice in the utilization of these energetic materials. And it's critical that we have a lot of coordination from the personnel who design and test these weapons, the personnel who utilize them out in the field, and also their commanders, who are the ones who decide how this is going to be organized, how the people are going to be trained, and how the operations are going to be conducted. So there's a lot of coordination involved. If you have interest in working in this area, my advice is to either get an engineering degree, or if you're working toward that, stay in that area and achieve that degree, because after that, what you'll need to do is you'll need to go online and look for federal civil service jobs regarding work at one of the services laboratories, or possibly even one of the Department of Energy laboratories. I selected this project that I worked on regarding designing and building barriers against explosive attack on civil structures, and even followed up by vehicle attacks. This particular project was an interesting one to me because the contractor came to me and said that the Nuclear Regulatory Commission had given kind of an ultimatum to nuclear power stations to come up with ways of defending themselves against possible attacks by people that would bring explosives in and large vehicles and try to penetrate into the protected areas at a nuclear power station. And this company had been told by some other people that it really wasn't possible to use barriers to protect against blast. And I could understand that a little bit because, you know, a barrier only protects against a blast wave whenever the item to be protected is within the shadow area of the barrier. And so protecting a nuclear power station with barriers and so forth against the air blast wave is kind of a tall order. But that wasn't what they were trying to do. They were trying to come up with a way to prevent incursions into the protected areas at nuclear power stations. And that's a different problem. So what you have to do is you have to come up with something that, given the limitations of explosive quantities, that the bad guys can't blast their way through a barrier system and allow, at that point, a large vehicle to be driven straight into the protected area. And in addition to that, the contractor that contacted me wanted to be able to build a barrier system that was modular. That was their idea, because they didn't want to build all of these barrier blocks, the modular pieces, or the barrier itself at one point and ship it across country, which would be very expensive to the different nuclear power stations that would be customers. And they also didn't want to have to build them permanently on site, because that would be expensive also. What they wanted to do was to be able to certify local concrete casters to build the individual parts of the modular system, and then ship them a very short distance and install them in place. Now that, puts some dimensional and also weight sorts of restrictions on what we could do, because they also wanted to try to build these portions of the modular system that would fit on the back of a flatbed truck and not require a permitted move. So that was a tall order. So based on experience and education to some degree, and also some test work that we had done, I began with the assumption that this system would have to have a concrete absorber, blast absorber, that would surround a steel frame that would be on the inside, and not just rebar, but actually a steel vehicle barrier. Because the whole idea would be that the concrete itself would defend against the blast. The concrete would be fragmented and blown away by the explosive attack. but it would protect the steel on the inside that formed the vehicle barrier. Now, I'd seen this happen in testing and work on other things where, turn the card over. I'd been trying to come up with ways using a single blast to penetrate a barrier. In other words, take out the rebar and the concrete and anything that might be inside of it. And I knew how difficult that was to do. It takes some sort of a tandem warhead to be able to do that. So in this case, what I decided to do was to figure out how much concrete and the dimensions of a concrete barrier, how much it would take to be able to defend against the threat that was given to me. And also what size and what type of steel barrier would work well once the concrete was stripped off of it. The steel was deformed a little bit, but still had to have the capacity to stop the threat vehicle. So it ended up being a very challenging requirement to do this sort of design. And I started thinking about, okay, how am I going to not only come up with a design, but verify that it worked? With that in mind, I used a combination of shock hydrodynamic analyses that if you took my Theory of High Explosives course at Missouri S&T, you would understand a little bit about the type of analysis that requires. Also, I used a piece of software called ConWeb. It's a U.S. Army Corps of Engineers piece of software. It's restricted access, unfortunately, after 9/11, but if you're working on a project that has to do with government systems, you can probably get a hold of it. I used ConWeb, to come up with a way to evaluate the crater sizes in the barrier itself and also in whatever surface the barrier was placed on. Using that and the contractor's decision that they wanted a modular system, I settled on the idea of having individual barrier blocks and use the height and size to come up with the weight that could be transported on a flatbed truck, a common carrier truck. One of the other requirements that I didn't mention before was that if the barrier wasn't anchored to the ground, we needed to figure out a way to determine about how far it might slide based on the surface that it was on. If a vehicle hit it before an explosion or in combination with the blast, so let's say if there was an explosive on a vehicle, in other words, a vehicle-borne IED, or after the blast, how far could a vehicle, once it hit the remaining barrier system, penetrate into this protected area? So what I did was I used an impulse momentum impact loading analysis, something that kind of came out of my mechanical engineering background, but is still, I think, something that those of you who have been through the mechanical engineering courses at a university would understand. It's a fairly simplistic design. It uses coefficients of friction, and it also uses, as I say, the impulse generated by a vehicle, the velocity and its mass, and also the amount of momentum that vehicle would have, and then the combination momentum of the vehicle and the barrier once the vehicle hit the barrier and started forcing it to slide. And at that point, determined that using two steel bars of a particular size located in a particular place in the center of the barrier system were strong enough to resist this. Now, that doesn't mean that that's the design we ended up with. It's just that at a minimum, 2 bars would work. And for various reasons that I won't address here because of their sensitivity, that's not the actual design that was finished with, that they actually deployed, but it works. The nice thing about that calculation was that you can put it on a spreadsheet and very quickly play with the inputs and see what's going to happen, what sort of sliding distances you have. You can change the friction coefficients very easily, and it's a very conservative analysis, which the NRC liked. We did some subscale testing of the components and the ideas at the experimental line there at Missouri S&T, but because it was a straight, off the paper analysis with some subscale testing, we decided that we needed full-scale tests to validate this. And those of you that have done design work for blast resistance understand the reason and the need for this. It's because even some of the best software out there doesn't fully give you the actual air blast and also cratering and so forth, all of the combination of different factors that are involved in tearing apart a system like this. So we took the system to a military base range. It's too big to handle the kind of blast that was the requirement. So the military allowed us to use one of their ranges down in the southeast part of the United States. And you can see in the photograph here, this is an after photograph that is part of the analysis that we did later on after this first test. We did several tests. One of the things we found out in the first test was that the metal pins that we used to hold the modular blocks together could possibly be ejected during a blast like this because of the rotating or rolling momentum that the blast added to the block that was under attack. And so we had to come up with a way of allowing the pins to be inserted in the field as you're building the barrier system, have the pins be protected against some sort of removal or small blast directed at them, and then also have them so that they would not be ejected during a blast. Eventually, everything was accepted by the NRC, and this system has been deployed at numerous utilities, nuclear power generating stations in the United States, also at facilities belonging to the U.S. Department of Energy and the U.S. Department of Defense. So it was a success. As I said, I don't think the military services will ever not need energetic materials, but they are constantly looking for new materials and new applications of the older materials. So these are the kind of areas to focus on if you are wanting to try to find a job working for one of the services or for the federal government. That's the key. If you work in those areas, I think you'll be a much easier hire for them. So thank you for your time and attention.
Well, that's an interesting insight into how explosives can be used in military applications. Our question and answer session with moderator Travis David-Saver, ISEE board member and emerging professionals section chairperson begins now. So take it away, Travis.
Thanks again, Alistair. Without our sponsors, we would not have been able to bring you this 10-part, 5-night free webinar series. Now let's talk live with our panelists, who include Jason in Missouri and Dennis in Mississippi. And they're ready to answer your questions about how we use military explosives. Please send your questions into us via the question and answer box, and let us know where you're from when you ask those questions. If you have a question that's directed to one or either of them, let us know, and we'll make sure it gets to the right person. Our first question this evening is going to go to Jason from Evan in Ohio. And Evan's asking what criteria are evaluated after a test to determine a vehicle or structure's resistance to the blast effects.
Well, that has to do to some degree with what the customer wants. But typically the sorts of things that you would evaluate would be, what is left of the protected structure, what sort of damage was done, either impact damage or blast damage or both to the exterior part of the structure that you're protecting. Also, one of the things that some people don't usually think about, if that protected environment had humans in it, then you'd also need to have some sort of instrumentation to determine the accelerations that those humans were subjected to because of the blast. Like, for example, a guardhouse or something where people would be expected to continue to have cognitive functions for several, within a few seconds after a blast. If they're subjected to really strong blast loads, even if they're not severely injured, they may be dizzy or fuzzy for up to a couple of minutes afterwards. So you have to look at all of those things in addition to the damages, the physical damages that are done. We usually do instrumentation on the outside too, to look at blast vibration as well as what we would call field air overpressure.
All right, Dennis, what type of evaluations do you do in your role?
Yeah, very similar things to what Jason just mentioned. It really does depend on the sponsoring agency and what their end needs are. It could be any of a number of different things. Usually there are prescribed parameters that the interested parties are wanting to quantify, and a lot of times that winds up being applied air blast loading for above ground structures, could be a ground shock loading for buried structures. And then, as Jason mentioned, there's an awful lot of emphasis on personnel safety. And so if we have, say, for example, armored vehicles that are being subjected to blast loadings, then often what we'll do is work in conjunction with some of the government agencies whose job it is to not only retrofit current vehicles, but also to improve designs for future vehicles as well. And so there have been actually quite a few improvements that have been fielded to vehicle types that are already in the field. A lot of seating, for example, improvements have been made. And I think a lot of lives have been saved. A lot of injuries have been reduced because of this.
All right. Thanks, Dennis. Our next question is from Dwai Handoyo. And the question is for both of you. And what is the comparison between military and commercial explosives, especially in the strength of these explosives?
Yeah,
let's start with, go ahead, Jason. We'll start with you.
Oh, okay. Well, talking about strength from an explosive standpoint is an interesting topic, and it's a very good question, because in the military, they're interested to a large degree in explosives that have great brisance or shattering effect. And, they create a very strong shock wave, in addition to gas pressure that after the shock wave passes through tends to cause parts to fragment more or come apart more than they would have otherwise. But in mining and quarry blasting, of course, they're not quite as interested in brisance as they are gas pressure and large volume of gas. And that's one of the reasons why a lot of quarry blasting explosives are either ANFO or ammonium nitrate based explosives, because of that large volume of high pressure gas that's created. And you do get some brisance, but not nearly as much as with high explosives such as TNT or C4 or some of the other ones. That's, I think, from a strength standpoint, if that's what you're talking about, that would be what I would say is the difference in brisance.
All right, Dennis, what about you? What are your thoughts?
Yeah, again, echoing what Jason said, the military explosives, they also tend to be engineered for more effect, say per pound. Can you get more effect from a particular munition, a bomb or a shell or what have you? And so, what's the maximum effect you can get for, a pound of explosive? And I don't know that it's terribly different in the mining industry, except for the fact that, again, you don't necessarily, I think, have as much in terms of the constraints on the relative mass of explosive, probably a little more leeway there. I will say that we utilize a lot of commercial blasting agents and other materials, if for no other reason, just the fact that one of the things that we really appreciate is how highly engineered a lot of those materials are. Sometimes you're not thinking that some of the blasting agents, they may not look as fancy as some of the high explosives, but we've been impressed with how well engineered they are and how consistent the results are. So again, I don't know that you can really compare, apples to apples. In this case, I think they both have their place, and there are well thought out reasons for using both.
All right. Our next question here is for Dennis, and it's coming from Tom in Ontario, Canada. How did you get hired in blasting research with a degree in geophysics?
Well, obviously they were pretty desperate at the time. But, yeah, I mean, the way it works with the U.S. federal government anyway is they classify you depending on how many hours of particular coursework you have. And so you don't necessarily have to have a degree in physics, for example, to be qualified to be a physicist. And I actually was hired on by the government account as a physicist because I had enough hours of physics and math to qualify. And once the government says you're a physicist, well, you're a physicist now, whether you like it. And so that's really how that came to pass. In practice, at least in our organization at the Engineer Research and Development Center, it's fairly invisible most of the time as to whether or not someone is an engineer. Most people are engineers, or a physicist, or a physical scientist, or any of the other technical fields. The sort of thing that evens out the playing field a little bit is nobody is really 100% qualified to do that job coming out of school. And so you have to learn some things. I think in a lot of ways the geophysics gave me a good background. The engineers, kind of make rude comments about my drawings, but that's okay. It's actually fairly seamless in most cases, and kind of hard to tell a lot of times. Except, the physicists tend to be a little more strange than the engineers on average.
All right. Well, Jason, our next question is for you, and it's coming from Brian in Kentucky. Since you taught explosives courses at Missouri S&T, can you briefly describe what a graduate student would expect from that curriculum?
Sure thing. Well, if you have come into an explosives graduate degree and you have sufficient background already in basic blasting and understanding explosives and so forth, then typically a lot of the work would be just like any other engineering graduate degree. Most of it would be research and busy working on, at the time I was there, and I think they still have a requirement for a written master's thesis. I know some schools have done away with that, but I believe at S&T they still have that requirement. So you have that major research paper that you have to do, in addition to doing quite a bit of work assisting whoever your advisor is with actual training of undergraduate students in hands-on drilling and blasting. And I think that's one of the things that S&T does that there are very few other universities that do that. They actually allow the students to do work with explosives on campus. So one of the roles of a graduate student there is to assist and sometimes to help teach those classes and to train the undergrads in how to do that while you're working towards your own degree. So it's a lot of fun, I think, very challenging. There are always new ideas, new questions from those new minds that you're working with. So it's I can highly recommend it if you're interested.
All right. Well, thanks, Jason. Our next question is coming for Dennis. It's from Philip Davis. Philip is asking, in your experiment with magazine testing, what quantity of explosives were typically being used, Dennis, to test those magazines?
It varied depending on what the storage capacity might have been at that particular point in time. Here, I think we were going with anywhere from, say, about 700 pounds to maybe 3,000 pounds of C4. And that is to generally model, say, a full-scale event where you may have, say, up to 500,000 pounds of TNT equivalent material stored in one of these bunkers. And so it still winds up being a fairly large amount of explosive just because of the massive size of some of these explosive storage facilities that we have to evaluate.
All right. It's a lot. That's a lot of explosives, even though it's only a small representation or a scale model for what you really get to test that against. All right. Our next question is for both of you, and it's coming from John in Colorado. How many jobs are there doing blasting research for the military? And I'll start with you, Jason.
Well, I really can't answer that very well. I might have to slope shoulder that off to Dennis, because whenever I was actively helping students look for jobs like that, it varied greatly from year to year. And a lot of it had to do with the strength of the defense budget at the time. The organizations that were hiring engineers had projects that they needed to do. And when the projects were funded, they needed people to work on them. And they, in most cases, would prefer to have people in-house doing that sort of work rather than hiring a contractor to do it. Dennis, have you got any other insights on what it's like today?
Yeah, Jason, as far as, more recently, we did go through a fairly long period of time where we had relatively few people hired. I think there was so much, I don't know if you want to call it over hiring back in the Cold War era. But, after that sort of settled out, now we see a fairly steady demand for new researchers. I know that at ERDIC and at some of our sister organizations, we're always looking for people. Generally speaking, if we find someone who is a good fit, we're always told, hire them. Don't worry about if you even have a specific project lined up, just hire them. We'll figure out something to do with it. So I think it's a good time. Even with COVID and other crazy things going on in the world, there's still a lot of demand for that type of research.
All right. Well, thanks, Dennis. Our next question here is coming from Scott. And Scott's asking, with regards to energetic compositions, what role are nanomaterials playing in improving energetic efficiency? And I'll start with you, Dennis.
Yeah, actually, I'm probably not the best person to ask something like that. Jason might well know more than I do.
All right.
I hate to say that we're bottom feeders where I work when it comes to things like this, but what we do is we don't really get involved in the formulations ourselves so much as we have some agency who is developing materials like that, and then they want to test the effects of those energetic materials, and that's where we really start to get involved. Now, having said that, there still continues to be quite a bit of work being done in that area, but maybe Jason can shed further light on that particular topic.
Well, from what I've seen here recently, the sort of work that's being done is a lot of basic research. I've seen a request for proposal already from different organizations for improvements in energetic materials using nanomaterials. The ones that I was involved with and that I can actually talk about had to do with things like nano aluminum. As some of you realize, aluminum, if you get it very pure aluminum that's not oxidized and you get very large surface area, in other words, very small particles of aluminum, very many of them, it's a very energetic material by itself. And if you can cause that aluminum material to be deposited in such a way that it still retains its nano quality, and this very large surface area per unit mass, but you have a way of protecting that from being oxidized until you want it to be, have a very very energetic, highly controlled material for, it may not necessarily be a weapon system. It might even be something that I've seen recently, and that's in flare research. The military does a lot of work with different types of energetic flares as drones and decoys and ways of disguising things and ways of marking situations or marking material or marking systems. So there is a lot of work being done on energetic nanomaterials, and as Dennis was saying, I think it's a big up and coming area right now.
All right, thanks, Jason. Our question here, we have a couple minutes left, and our next question is coming from Hannah in Minnesota. And Hannah's asking if you have any advice for someone who is about to start an engineering job working with explosives in the military.
Well, I think the thing to do is to make sure that you keep safety overall front and center when you're going through your training. Another thing is to realize that if you are doing a job, for example, like EOD, explosives ordnance disposal, that may have a little bit different bent than explosives engineering. In other words, you're going to be, if you're an EOD, for example, you're going to be learning in extreme detail different weapon systems and how they work and how to enable and disable them and so forth. And you may not learn quite as much about the details of the explosive materials themselves. as you would as an explosives engineer. But don't be disappointed. I mean, it is still a very active and exciting area. If that's the sort of thing that you're getting into in the military.
All right. We're just about out of time. We're going to squeak in one last question here. Dennis, what's the most interesting project you've gotten the opportunity to work on?
Yeah, that's a tough question because there've been so many of them that really have been interesting. Going all the way back to my early days when we were doing, million pound plus testing out in the deserts in the U.S. I'd say probably overall, a couple of years ago, we had the opportunity to participate in a 6-nation explosive test in Sweden. That was probably overall the most interesting and satisfying, just because number one, just the opportunity to work with a lot of great people in R&D from the different countries, and then also it was just a very interesting test. Got to see a lot of protective structures evaluated from the various countries, and again, just the people that we were able to interact with. So it was tough getting everything worked out, but it was really rewarding, and we wound up having a great success.
And how about you, Jason?
Well, I think the most interesting project from a hands-on standpoint that I've had was when I had a contractor come to me and ask me if I could do some testing for him using explosive form penetrators, the weapons that Dennis described a little bit earlier. And he said, sure. So I started searching around and trying to find one. And of course, the Army wasn't just going to give me weapons like that. So I had to design and build my own to use for the testing. And we did it. In fact, I got a bunch of students involved, and some of them are fairly well along now in their careers in the explosives community. And I think we had a really good time doing that. So that was probably one of the most interesting I've done.
Awesome. Sounds like a lot of fun. And it sounds like you probably weren't able to acquire most of your materials at the local hardware store. So
I was. I did.
You did.
Yes.
All right. Well, thanks, guys. I want to thank all of you online here for joining us tonight, this morning, or whatever time it happens to be, wherever you are in the world. Thanks for a great discussion, Jason and Dennis, and for helping put together this session about how the military uses explosives, and for being on our panel.
So thanks, Travis, and thank you for watching this episode of the ISEE Explosives Everyday series. Explosives are the ultimate power tool that help mine the minerals and materials that are used in creating many of the products and roadways we use each and every day. They help keep our towns and cities safe from avalanches. They are used to shape and improve the environment, and also military and demolition applications. And they're in some of our favourite TV shows, movies, sporting events and concerts. Our job as professionals in the explosive industry and at the ISEE is to ensure explosives continue to be handled and applied in the safest way possible, and to continue to provide the resources and tools needed to help advance the science and art of explosive engineering. If you're interested in finding out more about the International Society of Explosive Engineers, please go to our website, isee.org. You'll find information about membership, our chapters around the world, and other useful links, including a calendar of upcoming events, as well as conferences and meetings in our industry. Another great resource is the World of Explosives, where you can find information on using explosives safely, the most frequently asked questions from homeowners about blasting, how blast vibrations affect structures, and all the planning that goes into each blast. It's also home to Explosives the Power Tool. This is a video series covering the history of explosives and the technical advancements that have been made possible because of them. To check it out, visit explosives.org. Once again, a special thank you to this episode's sponsors, LDE Global, Dyna Nobel, OPIT Blast, RMAG, APT Research and Strauss, and to all our sponsors throughout the series. Before we go, here are a few short words from one of our series partners, OPIT Blast.
5, 4, 3, 2, 1. From now on, your blast designs will be perfect. OPID Blast presents the best blast design software simulator. Securely store all your projects created in the OPID Blast in the OPID Cloud, allowing staff to access all the information using the OPID app, OPID Dev. The best value for money on the world market. The definitive solution for measuring borehole deviations in quarries and mines. Efficient for 360-degree measurements. OPID Blast. With us, it's possible.
So that's it for this episode of Explosives Every Day. If you like this content, be sure to like and subscribe to our YouTube, Facebook and LinkedIn pages to stay up to date with all the latest ISEE happenings. And be sure to check out all 10 of our episodes highlighting the different ways explosives are used around the world every day. On behalf of the ISEE, thanks for watching and we'll see you next time.